Good day, dear colleagues. I present a work, pattern handling for quantifying hardware components of signature-based cybersecurity systems. When building cybersecurity systems, the signature-based approach is still relevant due to its feature of mathematically exact pattern matching. Here, patterns are the fixed sequences of characters which are parts of signatures. Reconfigurable accelerators based on FPGA are now widely used to accelerate the information security tasks. There are a huge number of technical solutions to build hardware matching schemes. A lot of approaches based on different technologies, the modifications, techniques, tricks. It is not a trivial task to choose the optimal solution for certain conditions. Earlier in our previous work, a method for fast quantification of technical characteristics of such systems and their components was proposed. It based on so-called estimation function and allows to predict hardware costs and performance of a given matching scheme and a given pattern set to be recognized. When creating estimation function, it is very important to be able to effectively handle with the patterns. We propose to present the pattern set in such way, namely set of patterns and a set of their properties. The follows pattern ordering technique is also proposed. Let us sort the patterns in a set by their length and distinguish groups or batches of patterns having the same length. Let us define the distribution function as a number of patterns in the corresponding batch. Proposed technique allows easily to find such values as the total number of characters in the pattern set, the total number of batches, and so on. Let us consider the estimation function for the hardware costs of the base CAM, basic content addressable memory scheme. As we can see, this expression depends on the given pattern set P, as well as on the properties of the FPGA device given. The pattern set properties are the length of the shortest pattern, the length of the longest pattern, pattern length distribution function, total number of patterns. The FPGA properties are the number of inputs of the load for a given FPGA and fan-out load property of the given FPGA. Let us test the proposed pattern set formalization with help of the parallel combining method. The essence of this method is to join together several different matching schemes and distribute the pattern set to be recognized between them in order to maximize the advantages of every matching approach. Here we can see the results of experiment 2 matching schemes, namely BSCAM and the large Bloom filter, are joined in parallel to recognize a signature database from the intrusion detection system node. We can see a pronounced minimum at a certain pattern distribution point when the resulting device consumes about 30% less hardware resources than any of the combined schemes consumes alone. Unfortunately, we observe such a nice picture not every time. More frequently, one of the matching blocks always, for any pattern distribution, shows better results compared with the entire module that consists of both schemes. How can we predict if the parallel combining gives a positive effect or not? A lot of experiments were conducted to determine the follows two conditions of the successful parallel combining. Was noting that the obtained conditions could not be found without using the fast quantification method, which in turn would be impossible to use without the pattern set formalization proposed in this work. Thank you for the attention.